working group for HTTP for maybe 8 years or so. So I've been here. This is the third time I'm here in this dev room, even if we have different rooms every time. But anyway, so I've been talking about HTTP and HTTP2, and I'm here again to talk about HTTP2. And now from this angle, yeah, we shipped HTTP2, right? You all run HTTP2. How is HTTP2 doing, and did it really fulfill its promises? Did it work? Does it work? And where it doesn't work, what should we do about it? And just as a short recap then, HTTP over the web, or rather the web has changed in this way, you know. The number of objects have increased, the size of the data that we're getting from an average web page today has sort of, the development is going in that direction. Amount of data, amount of objects or requests, and they're all, not all, but a lot of them from the same domain. This is basically just facts about the web of today. A lot of objects, a lot of data, and a lot of those objects are on the same site. And we have this head of line blocking problem originally in HTTP 1. Then we need to stand in one of these lines. We have a limited number of lines. We don't know how fast the line is, you know, which line in the supermarket is the fastest, you know, which one is the trainee in the front, which is the slow customer in ahead of you. You don't really know. We have that problem in HTTP. We have that in TCP. Sorry? I can speak louder. Yes, so the solution to that problem in HTTP 1 was this guy, HTTP 2 guy. So to fix the problems we had with head of line blocking and the number of objects, or make HTTP deal better with that large amount of objects, we introduced multiplex connections in HTTP 2, and basically then you can set a lot of separate logical streams over the same one physical stream. Yeah, and a large amount of them, which basically is 100 in basically every case. So when you want to send one image, the just-in train, that is sort of consisting of a number of frames, and you send another image which has also a number of frames, and you sort of frame. That's sort of, yeah, and they both go over the wire, same connection, different streams. And we'll come back to the just-in and IKEA train soon. And that means that when you're the client guy and the cloud over there, and you ask questions, because that's how HTTP works, right? You ask a question, the server sends it back. Ask and answer. But with HTTP 2, we don't need to wait for the answer before we can ask again. So we ask for a resource to get it back, but instead of waiting for that resource to get back, we can ask for more resources. And that some resources might then be slow or not. It doesn't matter, because we can keep on asking. The responses can then be differently paced. They can be fast or slow. It doesn't matter. They're all over the same connection, and they can send data as soon as it has it. Much better usage of bandwidth and usage of TCP in general. So that is HTTP 2 in 3 minutes. Okay, we made it. The RFC 7540 was shipped in May 2015. So we're approaching 2 years since the official RFC. So how does it really turn out to work in the real world? Well, basically every server you can imagine now supports HTTP 2. If you just check some config item somewhere. And all the open source ones, all the really big commercial ones. So server side, great. Browser side, all the browsers really that people are using are supporting it. There's a tiny percentage of that aren't supporting it, but that's diminishing. And that taken together then, server support, client support. Of course, that doesn't mean that the entire world has switched to HTTP 2. But, we have this telemetry data in Firefox or at Mozilla that Firefox can collect if you opt into it, and then we can sort of make we can see how Firefox is being used out in the wild among those who have opted in to this data collection, which I should just emphasize it's completely anonymous. We don't know which hosts, we don't know which users, but we can sort of get a hint by the amount of what is used. And we can see that HTTP2 is used in 30% of everything that is HTTP. And I would say that is a rather large share. And HTTP here is then all HTTP, that is HTTP and HTTPS. And as you might remember, we're only doing HTTP2 over HTTPS in Firefox and actually in all browsers. So it's actually perhaps more sensible than to see how big a share of HTTPS is HTTP2. And yeah, that's more than half. So I would say that, yeah, HTTP2 has taken on pretty good. And this is, of course, based on volume. Then you can deduce that, yeah, the major sites, the ones you're using the most, they are all using HTTP2. The Google, Facebook, Twitter, Instagram, blah, blah, all those big sites, they're using it. So by volume, that is way over half. But even if we're sort of checking out what sites are supporting on the big internet, we can see that 12% of the top 10 million sites. So yeah, that's not half. It's far away from a wide adoption, I would say, but it's getting there. And if you're sort of looking to the top sites, at least quite a few are there. And so more than 50% for your site. If you enable HTTP2 today, of course, you will see that the majority will use HTTP2 because, as you saw before, the browser support has been there for a long time. So everyone is going to use HTTP2 if you just let them. Right, and so that is the groundwork for this. HTTP2 fixes head-of-line blocking by multiplexing connections over the same physical one, and is getting deployed. That's good, right? It makes things better. But did it deliver? I mean, did the internet become a better place? Did we sort of did we make everyone's browsing or surfing or internet usage better? And is everything more enjoyable now? And of course, that is a tricky question to just answer to. But we can look at some metrics to see how HTTP2 is doing compared to HTTP1. Looking sort of, if we look under the hood. And when we're looking under the hood, it's obvious that we can look at some of the more sort of remote corners of the internet where probably most of us in this room, we don't really visit these corners very often. But people in third world countries perhaps, or with really, really crappy wireless networks like different mobile internet networks and so on. If we're then focusing, this is sort of the average round-trip time for Firefox users that we're collecting again in the telemetry. So, and this is clients running on the mobile, clients running on desktop. And if we're focusing on these guys, this 95th percentile, they're really, really far away from their servers. They're almost a second in round-trip time. That's a second. I mean, that's a really, really long time. So, as I said, the HTTP protocol is a lot of back and forth. Every back and forth takes a second. So, of course, we gain a lot by reducing the numbers of back and forth, asking a lot of questions at once and getting a lot of answers back sooner. It's much, much better, especially then for those in these really crappy areas of the internet, crappy by some measurement. And we can also see with measuring other things than internally in the networking parts of Firefox, we have a queue for outgoing requests, basically outgoing HTTP requests. We want to ask for these things. We want to send out these requests, but they're in a queue. We're waiting for a connection or some sort of an availability to send off this request. And it can be blocked by basically, we can't open, we're not allowed to open more connections, or we're blocked by something else internally. So, and then we can measure how long is the average time for a request sitting there. Quite a difference. So you will see that, again, if you're looking at these, I cut up a part of this table, but if you're looking again at the sort of the worst cases of the internet, the ones who had suffered the most, you can see that it's a drastic improvement. We're basically no longer waiting for outgoing requests. We can send requests much, much earlier. And 95th percentile we're seeing, I mean, that's almost a 100 times improvement. So of course, with a reduced number of round trips and much, much reduced waiting time, it will be a drastically improved experience for anyone on these networks. So I would say, yeah, sure. Looking at these numbers, and again, not many of us are going to be there regularly. So we might not have noticed, but there's a certain amount of people that have certainly gotten internet a lot better when they're using HTTP2. Another way to look at this same data, sort of, okay, this is how it looks in the good side and the bad side, sort of, this, and how it is improved in the crappy surroundings. Right, that data too. So how many requests are hanging in the queue longer than 100 milliseconds, which is sort of by, UX standards, is we want to have that as small and as little as possible. With H2, there aren't that many requests actually hanging for very long. Right, but so another way to look at this data is Human at Fastly made some great tests by running browsers in a test network where he would induce network packet loss, basically. Losing packets as you lose packets in the real world. That means you don't lose packets. It was sort of made to be a realistic simulation. And then we can see that, okay, here's a complicated graph. We don't need to go into the details, but these are basically, this is time in X, and we can see H2, H1 in Firefox, we can see H2, H1 in Chrome. And now we'll take a moment to see that Chrome is much slower, and then we move on. So this is the zero packet loss scenario, the ideal case for H2. Nothing is lost. H2 is just faster overall. Going into a really crappy network surrounding, 2% packet loss, which is quite a lot by network standards. You don't have that. This is not your ordinary Wi-Fi at home. You wouldn't want this. But a fair amount of traffic in the world is still suffering from this. So this is still a scenario that is happening, and we need to sort, how does Firefox, how does H2 and H1 compare in this nasty surrounding? And if we're then looking at the same colors here, we see that H2 performs much worse. The Firefox H1 is there, Firefox H2 is there, and this is then worse. And clearly, introducing packet loss at the rate of about 2%, H2 does not serve as good as H1. That's not as fun, right? Or shown as that. No, not good. But what do we do about that? Or rather, why is that? Why do we have that problem just because of some packet loss? We have one thing. We write HTTP2, everything over one connection. We have logical streams over one physical stream. One connection versus the previous H1, we had 6 connections. Having packet loss, there's a much bigger chance that one of the connections are actually sort of surviving when you get packet loss. So you have 6 times larger chance that your connection is going to survive without sort of waiting for a packet loss. While if you have one connection, one packet loss means everything is halted until we find the packet again. So that introduces a fun head of line blocking TCP level wise. Lose one packet, everything is waiting. If you're getting 100 images from a website, you lose one packet, all the 100 images are waiting for that packet. Not ideal, right? So, TCP networking school class 1. we have an IP layer, we have a TCP layer, and we have TLS, and we speak H2, right? And the train, right? The Justin train and the IKEA train, they are sort of, on the different H2 frames sent over the network like this. We lose a packet, yeah. It just happens to be very unaligned with everything, so everything has to stop because everything is built on all of them have sort of being together in this. So we need to fix the TCP head-of-line blocking problem. We can't have 99 images unrelated blocked because one image single packet has been lost. So we introduce a non-blocking TCP TLS H2, right? Easy peasy. So we need independent packets then so that we can lose a packet and the rest can continue. And so they still need to be stream aware then, so we know that, okay, we lost one packet, but all the other ones that are related to other streams, they can continue. Just this stream is going to be halted, right? And then we need to sort of, but we need to resend that packet, right, like TCP style. But this could be introduced with a new protocol, like why have TCP then if TCP isn't good enough? And UDP, UDP doesn't really retransmit anything. So we could invent a new protocol, but no, we cannot, because that's the way the internet works today. We never introduce any protocols because we have so many crappy boxes everywhere that just says no. So that's been tried and tested many times before. There are many new protocols, but they have a really hard time to get deployed because there are so much crap on the internet blocking that. So and even then, even if we could fix TCP to do this, right? How's your Windows XP doing? Right? And even if we would ignore those two-digit users on Windows XP percentage-wise, doing things in TCP is still kernel jobs. Fast pace over the kernel development, TCP, right? Yeah. No, it will take ages to get anything into TCP too. So even if that's work too, and we should do that, but it takes a really long time. Introducing quick. So this is basically all of that over UDP. And by doing that, we don't have any TCP or head-of-line blocking anymore. And of course, we need to sort of implement congestion control, and we can do it differently than TCP. And in Quick, we also sort of we can remove certain restrictions we had in TCP. It's tied to there's 5 identifiers in IP, source address, destination address, and port number, blah, blah, blah. We don't have that in Quick. We can move them across interfaces easier. So basically, Google has done this. And it turns out that UDP is not as problematic as was sort of what we always thought that, switching to UDP is going to break half the internet, right? It's not going to work because there's so many boxes that are going to not allow UDP like this because we have never used UDP like this before. We use UDP for, timing and some other tiny things. Some like video and stuff, but we haven't done it at this scale. But Google proved it working. So basically then, networking school, these are all aligned, sort of. Losing one packet there, everything is aligned. We just wait for that just-in packet. The IKEA train can continue. We don't have to wait for the rest of the stuff. But of course, this isn't sort of easily done. Then the quick job, Google has deployed this. They have run this on the internet. If you use Chrome and Google's server, you have used Quick for, I don't know, a year already or so. So they have sort of proven that it works to deploy a protocol over UDP like this. So the work has started in the IETF, sort of HTTP2 style, to get that protocol into the IETF and make a standard out of it. There's a massive interest, and things are being changed. A lot of things are being changed, actually, in the protocol. So we'll see what happens. It is sort of a condition for it being adapted in the IETF is that it will also be made as a transport protocol, more available to transfer more stuff than just H2. There was an interim meeting in Tokyo last week. And there's going to be the IETF Quick, which is going to be quite different than the Google Quick, even if it's going to be the same principles. like Speed H2. They bring in the Google Quick, it's going to become an IETF Quick. They're going to be the same in principle, completely different on the wire and sort of the specs. Maybe early light test mid this year from some big vendors. I'm out of time. But this is not going to be HTTP 3, but it's basically HTTP 3, right? It's next step, but it's not called HTTP 3. And could have been TCP 2 perhaps if it's becoming a transport protocol for other things than H2, but it's not. And I like this picture. The Google guys especially appreciate when I call it TCP 2. No, it's not going to be that. It's just going to be quick. So then a fast roundup is that H1 wasn't really optimal, and H2 is binary. Multiplex fix a lot of these problems. It is getting widely adopted and used everywhere, especially then sort of if we count by volume by browsers. It makes sites faster. I didn't really say that, but it does. And quick is coming really soon, maybe. And basically H2 frames over UDP. That's the summary of everything you need to know. Thank you.
We do have like 5 minutes if you want to take some questions.
Yeah, sure. If anyone has any questions, we can do some quick questions before I...
Yeah, if you have a question or two, we can handle that. Yes, please. I'm gonna stop here first. Sorry, but I'm.
Can you please try to be quiet, the other ones, if you don't have any questions?
Hi. Any supporting curl for quick?
Sorry?
Any supporting lib curl for quick?
I will support quick in curl. Not today, no. But today, quick is sort of in a flux right now. So. What is quick today? The quick Chrome is using today is still Google Quick, and Google Quick is going away and going to be replaced by IETF Quick. So there's really no point in me going forward to do Google Quick when the IETF Quick is coming, and IETF Quick is still not really solid. So it'll come, but not yet.
Hi. Yeah, sorry. Hi. I'm wondering, I mean, the UDP doesn't fix fragmentation of packets in sort of any servers or anything in between. Has there been any work or any tests how fragmentation affects UDP and obviously TCP as well?
I'm not sure I followed the question. I mean, UDP, it works like this, and in a real live deployment, browsers are going to raise TCP against this UDP version. So in those few cases where UDP doesn't really work, they'll just use the old style anyway.
Merci beaucoup. Thank you. Sorry. I want to see you here. Well, I think it's very hard to ask questions. And why not?
Yeah, it is.
Sorry, what happens with old websites that used to do splitting of the images? Are they slower with HTTP 2?
No, they're not slower, but they're not necessarily faster either. I mean, there are certain things that you could reconsider doing when you're switching to H2.
Okay, so now we don't need to do that anymore, the splitting.
It's not that easy to say yes or no, but, but yeah, maybe.
Thank you.
You have a question? You can give me the hat on it.
You want to wear the hat during the question? Hello. You didn't really talk about it, unfortunately, but obviously you use quite basic forward error correction for packet loss. It's very basic compared to other IETF documents, such as RTP. Do you know if there are any plans to use much more advanced error correction methods?
What I think is that forward error correction is out.
It's out completely now. Okay. Why is that?
Because they did a lot of work on that within the Google effort before, and they sort of deemed that not sufficiently good to continue.
Even on high latency links? That's interesting.
Yeah, because the waste in bandwidth is really hard to make a trade-off. So I'm not the one to really answer the question about exact details there, but I know it's been sort of put to the side.
Thank you.